Okay, thank you very much. So thank you so much for the invite. And I'm really terribly sorry I'm not there. My whole family is sick at the moment. But I'm happy to give the talk on Zoom instead. So indeed, I'm going to talk about geometric invariant theory for non-reductive groups. And actually, most of this is just going to be a sort of general introduction to the idea of geometric invariant theory for non-reductive groups. And at the end, I'm going to talk about a few of my projects related to this. But I really want to start with a sort of very general overview. So the plan for today's talk, and please just interrupt me whenever you have a question. I can hear you pretty well, I think. So the plan is that I'm going to start by just explaining why we care about group quotients, and the reason that I care is moduli spaces. And then I think the second part of my talk is going to have some overlap with Anna Maria's talk from yesterday. So I'm going to talk about Hilbert's 14th problem, which is related to quotienting affine schemes and sort of what goes wrong for non-reductive groups, which I think you saw a lot about yesterday. And then after that, I'm going to just give a very quick recap on what happens in the good case when the group is reductive. And then finally, we're going to talk about sort of the easiest non-reductive group, which is just the additive group. And then the last section is then talking about sort of a general framework for non-reductive geometric invariant theory, which we call relative non-reductive GIT. And I'm going to discuss some applications to representations of quivers with multiplicity. So these are, rather than looking at representations of quivers over a field, you look at truncated polynomial rings, and you see, in this case, non-reductive group actions appearing. Okay, so let me begin with the introduction, which is about moduli spaces as group quotients. So yeah, moduli spaces very roughly should be thought of as geometric solutions to a classification problem. And the classical construction is as a group quotient. So first of all, you over-parameterize the objects that you're interested in. So you describe all objects, possibly plus some extra data, using some parameter space. And then you want to sort of encode the symmetries, so whatever extra data you've added, by an action of a group on this parameter space whose orbits ideally correspond to the equivalence classes that you're interested in. I'm going to give some concrete examples in a minute. And then you want to construct a quotient. So in algebraic geometry, assuming that G and X are both algebraic varieties, we use geometric invariant theory. And I'm going to say more about this, but basically there's two ingredients. So firstly, you remove some orbits, which are called unstable, and then you glue some orbits whose closures meet. So actually, really, the space only parameterizes the closed orbits, and these correspond to the polystables that Milena was just talking about. And then the last step is actually you have to interpret what you've got. So this stability and gluing often admit moduli theoretic interpretations. So this closed orbits correspond to polystables, for example. And stability, we also saw corresponds to this slope stability. So that also comes from a GIT type condition. Okay, so let me just give some very basic examples before we get into the meat of it. So to start off with, well, actually, let me keep my little list here. You can think about the easiest moduli problem is to look at one-dimensional vector subspaces in a fixed vector space. So then to parameterize them, you can choose a basis vector. And so that's parameterized by all non-zero elements in your vector space. And then the symmetries, well, you want to modulo by change of basis, which is just scalar multiplication in this case. And then the quotient is just the projective space, and this is actually an orbit space. So this is about as nice as it could be. But a little bit more of a complicated example is if you look at matrices up to conjugation, then this can be described as the orbits for the action of GLN on m by m matrices by conjugation. And there's actually a quotient which is given by taking, well, I guess the coefficients of the characteristic polynomial. But this quotient already identifies some distinct Jordan normal forms. I will come back to this example later, but it identifies these two Jordan normal forms. So here we've got the same eigenvalues in both cases, alpha and alpha, but in one case we have two Jordan blocks, and in one case we just have one Jordan block. And actually, there's a generalization of this, which is moduli of quiver representations, where now you're sort of looking at linear data encoded by a directed graph. So I've drawn a sort of picture here. So actually, the case where you just have this loop quiver corresponds to a vector space with an endomorphism, and that is precisely this matrices up to conjugation after you choose a basis. But more generally, you can look at basically tuples of matrices up to simultaneous conjugation. We'll return to this example a little bit later. And then another classical example is to look at hypersurfaces in projective space of a fixed degree D up to a change of coordinates on the projective space. And so here, these are naturally parameterized, so you can just take degree D homogeneous polynomials. So actually, you don't want to take the zero inside here, and you want to projectivize because rescaling the polynomial doesn't change its zero locus, right? And then the group action is just the automorphisms of Pn acting on X. And then there is a quotient, but in this case, you actually only get a rational map from X to the GIT quotient. And it's defined on this semi-stable locus. So we will see a little bit more about this. And then there's also a generalization of this, which is now you can look at hypersurfaces instead in weighted projective spaces, for example, or more generally toric varieties. And the reason why I suggest these examples is because their automorphism groups are well understood by work of Cox, so they're affine algebraic groups. But the point is that actually they're not necessarily reductive anymore. So this group here was reductive, but if you look at automorphism groups of weighted projective spaces, we'll see they're not reductive anymore. So I am going to give the definition of what it means to be reductive. So don't worry if this is a word that you don't know. It's going to come in a minute. So let me say a few things about Hilbert's 14th problem, which is really the affine part of the story. So we've got an affine algebraic group, which is, well, if you like, just a closed subgroup of GLN. And it's acting on an affine variety, X. And so you actually, instead of thinking about the morphism of varieties giving you the action, you can instead think about the algebra homomorphism, which we call the coaction. And you can ask, well, is there a reasonable quotient? And then you have to decide what you mean by a reasonable quotient. I mean, I guess your dream would be that there would be an orbit space, but quickly you see that there are non-closed orbits which will stop that from happening. And in general, the topological quotient just won't be algebraic. So maybe the best thing you could ask for is a categorical quotient, so a universal G-invariant morphism from X in the category of algebraic varieties over K. And what's more natural from the perspective of GIT is actually to ask for what's called a good quotient, which is you also ask for a G-invariant morphism from X to some variety Y, and you ask that this is actually an affine morphism and surjective. And on the level of sheaves, it identifies the structure sheaf of Y with the push forward of the G-invariant functions on X. And then additionally, the good quotient should separate disjoint closed G-invariant sets. So of course it's going to glue some things. We've sort of agreed that has to happen, but you want that if you have closed orbits, then these should be separated by this quotient. Let me just say a few things. So just if you take a function, so a morphism from X, which is G-invariant, i.e. constant on the orbits, then if you look at the corresponding map on functions, then this actually factors via the G-invariant functions on X. So these are the functions on X which are constant on orbits as well. And I think you saw this yesterday, but let me just repeat. So Hilbert's 14th problem is really asking, so is this ring of invariants finitely generated? Because if it is, then you would want to take the associated variety for this. So if so, you can consider this map going from X to this X /G. So this is the notation for the GIT quotient, which is given by the spectrum of this finitely generated ring. And you could ask then, is this a good quotient? So there are several different answers to this. So firstly, we'll start with the good stuff and then the not so good stuff. So the first thing is if G is reductive, then the ring of invariance is finitely generated. And moreover, this quotient that you get is a good quotient. So actually, the case where G is linearly reductive really goes back to Hilbert. And then more generally, the general result is due to Nagata. And then, so I think this is the point that was really discussed yesterday, which is there are examples of non-reductive group actions where the invariant ring is non-finitely generated. But I want to sort of focus on more positive results, which is where you can get finite generation. So from now on, I'm going to actually assume that the characteristic is equal to 0. And this is really because unipotent or additive groups behave quite differently in positive characteristic to characteristic 0. We'll see this later on. But if we assume that K has characteristic 0, then firstly, there's an old result of Weizenbach, which proves that if you've got an additive group, so this is just K with addition, acting on an affine space, and the action is linear, so i.e. via representation of GA to GLN, then the invariant ring is actually finitely generated, which sounds great. But unfortunately, then when you take this induced GIT quotient, if you like, it's not going to have the properties of a good quotient. So for example, it might not be surjective. And so, and even if you want to say, well, let's just look at the image of this map, the image might just be constructible. So I'm gonna discuss some examples where this to show you what can go wrong. But there is a fix to this, which is sort of the beginning of non-reductive GIT, and this was a paper of which goes back to the work of Birksey, Doran, Hawes, and Cowan about 10 years ago, I guess, which says if you've got a unipotent group acting on X, still affine, and it extends to a what they call a graded action of U semi-direct product, a copy of the multiplicative group, and you have some sort of stabilizer assumption, then actually the ring of invariance is finitely generated, and this quotient turns out to be a trivial U bundle. So in particular, it is a good quotient. In fact, it's a geometric quotient. And so this is the setting in which you can really produce well-behaved quotients. And I'm going to talk about this in greater depth later on. So yeah, let me give you some remarks on these 4 different answers. So the first one, in the case when G is linearly reductive, uses the existence of what's called a Reynolds operator, which you should think of as a generalization of averaging over the group somehow, because if G was finite, you could sort of average over the group, and this would give you a way to associate to a function a G invariant function. But for obviously non-finite groups, you can't do that. But the idea is here that it's sort of a canonical projection onto the G invariance. And the second point of this result of negative was discussed yesterday, I believe. And so it involves really showing that for this example, that the ring of invariance can be identified with the Cox ring of a blow-up of some projective space at some number of points. And then, well, essentially, you prove that this is not finitely generated by showing that there's a Weil group action, which is which gives you this non-finite generation. But so I'm not really going to say too much about 1 or 2, but I do want to say a lot about 3 and 4. So this is going to come later. So for 3, to show that this invariant ring is finitely generated, you actually extend the action of GA to SL2. But this isn't enough. So instead, for 4, you don't extend it to SL2, you just extend it to the Borel in SL2, which is basically GA semi-direct product with a multiplicative GM. And you use this trivial stabilizer condition to find a slice. So I'm going to really explain these later. But let me give the definition now of unipotent and reductive groups. Or maybe I should pause, and if there are any questions, you can already ask them now. No, okay. I'll go on to the definitions of unipotent and reductive groups then. So as an affine algebraic group is unipotent. So there's actually many different ways to define this, but I'm just giving the easiest one. If it's isomorphic to a subgroup of the upper triangular matrices with 1s on the diagonals in GLN. So that's one way to define a group to be unipotent. And then a group is reductive if every connected unipotent normal subgroup is trivial. Another way to say it is you can construct a sort of maximal unipotent normal subgroup, and you can ask that this is trivial. So this is what's called the unipotent radical. And the other definition that came up is this notion of linearly reductive, which says that whenever you take a representation of G, so V is a finite vector space with a linear action of G, then it's completely reducible, which means that I can decompose V into irreducible G representations. So in general, that's not possible, but for certain groups it is. And so in fact, linearly reductive implies reductive, and the converse is true in characteristic zero. So if you're only interested in characteristic zero, then you can forget about the difference between these two. And yeah, as I said, there's this. So if you take any affine algebraic group, then you can consider its unipotent radical, which is a sort of this maximal normal connected subgroup. And then once you quotient by this unipotent radical, then the group that you get is reductive. So you sort of have the unipotent part. So this is the non-reductive part, and then the reductive part. So you have you can split G into these two pieces in a sense. So let me give you some examples. So the easiest example of a unipotent group is the additive group. So this is just the affine line where the group action is just addition. And you can see this as upper triangular matrices inside GL2 where you just have an entry here. And then this as you multiply these, this really gives addition here. And then the multiplicative group is linearly reductive. So this is A1 minus the origin, and now you're looking at K star with multiplication. Because if you have a GM representation, then you get a Z grading on V. And then by taking a basis, so these VIs are the vectors where T acts with weight I. And then you take a basis for each VI, and this allows you to decompose V into irreducible representations. So this is why it's linearly reductive. And the same is true as well when you look at a torus as well. So you could look at GM to the N, and then you get a ZN grading. And this is a general thing about actions of tori on affine schemes. Okay, a little bit more complicated is that GLN, SLN, and PGLN are reductive. I'm not going to explain this. It's just kind of important because these groups often appear when you want to construct moduli spaces. An example of a non-reductive group is the automorphism group of weighted projective spaces. So here, what I mean is that you take affine N space, N plus 1, sorry, and you take the GM action, which has weights A0 through to AN, and then you remove the origin and you take the quotient and you get this weighted projective space. So I will give you a concrete example of what this looks like in general, but you'll see that there are quite easily, you can get actions of additive groups here. And then another example, which is also interesting, is if you take a reductive group, then you can actually inside it find non-reductive groups, which are parabolic subgroups. So if you take a one-parameter subgroup, so a non-trivial group homomorphism from the multiplicative group to G, then you can construct an associated parabolic group, which is consists of the G and G, such that when you conjugate G by this one-parameter subgroup and you take the limit as T goes to 0, so what I'm really meaning here is take the map from GM to G and ask whether it extends to A1. And so you assume that this exists. So this is a subset inside G, and it decomposes again as, so you have a unipotent radical and then some reductive Levy factor. So let me make this a little bit more concrete in the case of GLN. So if I have a one-parameter subgroup and I'm going to assume it's diagonal, and it's got a constant weight omega 1 on the first block, and let's say the first block has size n1, and then you have r different weights, and you have weight omega r on the last block, and these weights are strictly decreasing, then you get a parabolic subgroup, which is block upper triangular matrices, where the block sizes are the block sizes here. So this Levy factor is these diagonal blocks, and then the unipotent part is this stuff on the strictly upper part. Okay. Let me say a few words about Mumford's reductive GIT. So the idea is that the local model for reductive GIT is always affine GIT quotients, which is given by, there should be a group acting somewhere here, I guess. So I have G acting on X, and I take the invariant ring. So G here is reductive, of course. So then I know the invariant ring is finitely generated, and so I can take the associated variety. So I just wanted to do one concrete example, which is what I mentioned a little bit earlier. So if you take GL2 acting on 2 by 2 matrices by conjugation, then you can ask, well, what are the G invariant functions here? So you're looking for conjugation invariant functions on matrices. Well, from linear algebra, you know that the trace and the determinant are both invariant functions. And so you can take polynomials in these, and this will be contained inside this invariant ring. But from another perspective, if you want to describe this invariant ring, well, you know that any conjugation invariant function or any invariant function will be constant on orbits and also on orbit closures. And every orbit contains in its closure actually a diagonal matrix, because you can so orbits just correspond to Jordan normal forms. And then if your Jordan normal form is not diagonal, then you can essentially act by a copy of the multiplicative group to make it into a diagonal matrix. So you can sort of degenerate it to a diagonal matrix. And so every orbit contains a diagonal matrix in its closure. And so to understand how these invariant functions behave, you can just look at diagonal matrices. And now the action of GL2 just becomes the permutation action of the symmetric group S2. And then, of course, we understand what this invariant ring is. So this is one of the few examples where you can really compute the invariant ring very easily. So we know it's the elementary symmetric polynomials. So we have this one, which precisely corresponds to the trace, and this one, which corresponds to the determinant. And so in this case, this GIT quotient that we get is, it sends a matrix. Oh, sorry, and there should be 2 lines there. This is very important. So it sends a matrix to its trace and determinant. So this double slash notation is very important because this is not an orbit space. And this is a good quotient, but indeed it identifies the Jordan normal forms where you have the same eigenvalue, but here you've got 2 Jordan blocks, and here you just have 1 Jordan block, because these have the same trace and determinant, but they're not, these orbits are distinct. So, but the point is that this orbit lies in the closure of this orbit. So that's kind of an easy exercise. You can take a 1-parameter subgroup, so a copy of GM inside GL2, which degenerates this one to this one. Okay. Let me state sort of a very general theorem about GIT, and then we're going to do it in a few more specific cases. This is still in this reductive case. So Mumford proves if you've got a reductive group G, and I'm just going to assume that it's acting on a quasi-projective variety, and with respect to a line bundle which has a G equivariant structure. So this is sometimes called a linearization. We saw well, sort of torus equivariant line bundle, well, torus equivariant sheaves in the previous talk. And so you can also talk about sort of G equivariant line bundles. Then, so you're just really thinking about this as you're lifting the action on X to this line bundle. Then there exists open sets and quotients of these open sets. So firstly, you have a semi-stable set, which is an open set inside X. And then it has a good quotient. And then inside the semi-stable set, there's a nicer set, which is a stable set. And this has a geometric quotient, which means that actually this quotient now is a orbit space. So you're not actually collapsing any orbits anymore once you restrict to the stable locus. I wanted to discuss a few concrete examples of this theorem in action. So the first is the one that we've already discussed, which is the affine GIT quotient. So in the case when X is affine and you take just the structure sheaf for your G equivariant line bundle, then the GIT quotient above is given by this affine GIT quotient that we saw just sending X to the spectrum of its invariant ring. And in this case, all points are semi-stable, so we don't have to remove any points. But we've already seen in this case that indeed you do have to glue some orbits. So we saw this in this example for matrices up to conjugation. And actually, sometimes this gluing can be very extreme. So for example, if you imagine that you're looking at X is AN, and you're looking at the standard action of GM by scalar multiplication, then every orbit contains in its closure the origin. And so in this case, the quotient is going to be just a point. But you can sort of see that as soon as you remove the origin, then actually you get a nicer quotient. You get a projective space. And so one way that you can do this is by imposing a notion of semi-stability, which will remove the origin for you. And this is what I refer to as twisted affine GIT. So it was introduced by King. And now what you do is you have an affine variety still, and you take the structure sheaf, but now you twist the G equivariant structure using a character row of G. So just a group homomorphism from G to the multiplicative group. And then this gives you now a quotient of only an open semi-stable set. And obviously this is going to depend on the choice of character, and actually how it varies as you move the character is kind of a very fun thing to try and understand, because there's very nice birational transformations as you do this. And you get a quotient which also depends on this choice of character. So I write it here. And what is it? Well, it actually turns out to be projective over the affine GIT quotient, and it's proj of a ring of functions which are only, rather than invariant, semi-invariant with respect to this row. And this is a graded ring, so it has sort of different pieces depending on what power of row you're sort of modifying by. And let me say that the nice thing about this situation is that, so in general, this semi-stable locus is just defined as being the locus where there exists some semi-invariant with n strictly positive, which is non-vanishing at that point. So it's just the domain of this rational map. But Alistair King proved that you can actually really combinatorially pin down what this is. So instead, you can define it as the points in X such that you have a certain inequality. So if you pair your character rho with your co-character lambda, then you get an integer, and you ask that this integer is greater than or equal to 0. And you only have to check this for one parameter subgroups such that when you flow down under this one parameter subgroup as t goes to 0, this limit exists, because of course X is affine, this limit might not necessarily exist, but you only have to check for those lambdas for which X exists. And so this gives a very concrete description of this semi-stable locus. And this is what's called a Hilbert-Mumford description. Okay, and then the other case, which perhaps people are more familiar with, is projective GIT, which is now you assume that X is projective, and I'm going to actually assume that X is sitting inside some projective space Pn, and I'm taking, well, O1 on Pn and pulling it back to X. And I'm going to assume that G acts by a linear representation, so it's acting on Pn by a representation G goes to GLN plus 1, sorry. Then what is the quotient in this case? Well, so you just basically look at the homogeneous coordinate ring of X. So forgetting the G here, that's this, a ring here, and you take G invariance, and then you projectivize, and you get a rational map from X, which is, basically induced by the inclusion of G invariants. And again, the semi-stable locus is defined sort of abstractly as points where there is a invariant function which is non-vanishing. But there's kind of a nice topological description, which is that you can work, instead of working in this projective space, work in the affine cone above it. Sorry, it's below in the picture, but usually you think of it as above. And you take, so you lift X to a point X tilde inside the affine cone, and you take its orbit and its orbit closure and ask whether the origin is contained inside there. So that's kind of a topological description, but then there's a very sort of combinatorial description, which is if you fix a maximal torus, then you basically just can compute the semi-stable locus for the maximal torus and then sweep out by the G action. And the semi-stable locus for the maximal torus is really just determined by the torus weights, because all you have to do is ask whether the origin is contained in the convex hull of the torus weights of X. Okay, so yeah, these Hilbert-Mumford descriptions are really explicit. So they're determined by torus weights, which in general are much easier to understand rather than computing rings of invariance, which is hard. So I should say that I mentioned that this notion of slope semi-stability came from this GIT notion of semi-stability. And in that case, you don't compute torus weights. I mean, this is too tricky. So often instead, what you do is you rephrase this condition or as a numerical condition, asking that for all one-parameter subgroups, you have a certain weight being greater than or equal to 0. So just like here. And that's this certain weight being greater than or equal to 0 is basically this inequality of slopes that you have. Because you can think about the one-parameter subgroup inducing for you the filtration of a vector bundle or a sheaf. Okay, are there any questions before I move on? Now we're going to come to the harder part, which is additive group actions and non-reductive GIT. So, I'm going to assume that the characteristic of our field now is 0, and you'll see why it's this proposition. So, for an affine variety, there's a bijective correspondence between actions of the additive group GA on X and K derivations on A, which are locally nilpotent. And how does this go? Well, you take an action. So this I'm thinking of as a morphism from GA across X to X. And you can consider the associated coaction, which is a algebra homomorphism. And then you take the derivative with respect to the t, so this coordinate on GA, and you evaluate it, t is equal to 0, and this will give you now an element in A. So this will then give you a k-linear map from A to A, and you can check that this is locally nilpotent. So what I mean by that is, rather than there being a global n such that dn of f is equal to 0, for each f in A, there's an n which depends on f, such that when I apply my derivation n times to f, I get 0. And so why do we need characteristic 0? Well, the fact that this derivative has enough information is because you're working in characteristic 0. In positive characteristic, you're going to need more derivations to understand this, well, higher derivations. But otherwise, you can go backwards by exponentiating. So if you exponentiate the derivation that you have, then you get a coaction. And then this coaction will define for you an action. And moreover, under this bijective correspondence, you can describe the ring of invariance as the kernel of the associated derivation, which is quite nice. Okay, so this derivation can actually be used to discuss when you can extend a GA action to an SL2 action. So, and yeah, I wrote some names here of various people who have been working on this. I mean, there's a much longer list than this, but I want to explain this theorem of Weizenbach in particular. So you can think about GA as sitting inside SL2 as this unipotent group inside the upper triangular Borel. You can ask, well, what's a quotient for GA acting on SL2 by left multiplication? So I've written the action here. Sorry if it's a bit small. You can easily see that the bottom row of the matrix is preserved. And so actually there's a natural map by sending a matrix to its bottom row. And so, of course, the bottom row, you can't have both being 0 because the determinant of this matrix is 1. And so it lands in A2 minus the origin. And you can really see that this is indeed SL2 modulo GA, because you can think about this as an SL2 orbit for the standard representation on A2, namely as the SL2 orbit of the point 1, 0 in here. And its stabilizer is GA. So this helps you to describe this quotient as A2 minus the origin. Yeah, the theorem that I wanted to explain about extending GA actions to SL2 is that in characteristic 0, any linear GA action on an affine space can be extended to SL2. And then using this, you can prove that the ring of GA invariance is actually finitely generated. Okay, so I wanted to sketch the proof because I think it's really nice and it uses some of the ingredients that we've seen. So because the action is linear, when we look at the action on the coordinate ring, which has these grading into different symmetric powers, this preserves the graded pieces, so it sends W to W. And so then if you look at the derivation, so D associated to this GA action, then D sends W to W as well. And so you get an endomorphism of W, which is nilpotent, and so you can describe it as a nilpotent matrix. So then you just pick a basis of W that puts this matrix in Jordan normal form, and you get some Jordan blocks again. I'm supposing that I have R different Jordan blocks of size N1 through to NR. Then each of these Jordan blocks will correspond to an irreducible SL2 representation. So as an SL2 representation, you can then write W as a sum of R different irreducible SL2 representations where the dimension of these should be Ni. And so the only SL2 representation of dimension Ni is you take the Ni minus 1th symmetric power of the standard representation of SL2. And so, of course, you have to keep track of this change of basis, but this gives a way to extend the action to SL2. Okay. Because so this is this n-dimensional vector space corresponding to the affine space that we were looking at. Okay. Well, I guess there's a dual somewhere. Yeah. Okay. So now we know that the action extends to SL2. Then what you can do is you can take this Borel construction, which is, so I'm just writing X for AN. You take the product of X by SL2 and you take the diagonal action of GA on this and you take a quotient. Now this quotient is actually isomorphic to just X and then cross the quotient of GA acting on SL2. Maybe I should put some brackets around this to make it clear that the quotient is just on this side. And I wrote down the isomorphism for you here. And so you see that actually this Borel construction is this variety X cross A2 minus the origin. And so now, using this Borel construction, you can compute the ring of invariance because you have that the GA invariant functions on X are the SL2 invariant functions on this Borel construction, which is just X cross A2 minus the origins. This is only quasi-affine, so its coordinate ring is not going to be finitely generated in general. But the nice thing is now that you can use Hartog's theorem to say that you can extend over the codimension 2 gap given by including A2 minus the origin inside A2. And so a function here extends to a function on X cross A2. And now we have an affine variety and we're taking invariance for a reductive group. So by, well, I guess in this case, it's really due to Hilbert, but sort of the ring of invariance is finitely generated. And so this sounds great, but we're going to see that there's a problem, which is that so even when you're in the situation that the ring of invariance for GA, the additive group, is finitely generated, the quotient that you get is not going to be a good quotient in general. So firstly, I'm sorry, I didn't give a name. So I'm going to call this quotient pi. So this map pi might not be surjective. And in fact, we've actually seen this in an example above because we took GA acting on SL2, then you can see that actually the invariant functions on SL2 are given indeed by the coefficients for the entries in the bottom row. And so the quotient that you should get is A2, but actually, of course, it only lands in A2 minus the origin. So because, of course, you're going to get always going to get, so this is affine, and so you're always going to get something affine here, whereas this is only quasi-affine, so it's landing in some open subset. So you could think, well, okay, well, let's just take the image to be our quotient and say that this is a good quotient. But that also fails because the image of a morphism of varieties is a constructible set. And in fact, you can fairly easily produce examples to see that you get a constructible set. So you can take, so all the actions that I'm taking are GA actions which extend to SL2. So I take GA acting on A2 via the standard action of SL2 on A2 by left multiplication, and I take 2 copies of that. So what does the GA action look like? Well, so on each block you have U sends x1 to x1 plus ux2, and it fixes x2, and then the same thing on this block with x3 and x4. And then you can ask, well, what are the invariant functions? Well, x2 and x4 are invariant functions, but then you also have this sort of determinantal one, which mixes the 2 different blocks. And so the GIT quotient, if you like, should be A3. But then you can see that the image, of course, misses the punctured line. So if x2 is equal to 0 and x4 is equal to 0, then this is equal to 0. So it never lands. So it misses this punctured line where lambda is non-zero, but the first 2 coordinates are 0. And so you only have a constructible set. So this is also not great. And then there's even more problems. I will list a few. So firstly, the pi does not separate closed orbits. So if you look at the GA action on now, I take the standard representation, I take sim2 of it. So this looks like a 3-dimensional vector space. I've written it down concretely here, and I've written down what the invariants are. So you get an A2 as the quotient. And you see that these invariants don't separate the closed orbits, which are given by looking at the orbits of the points 1 and then either plus or minus 1 and 0. So these orbits look like this. And you can see because of this x squared, x2 squared term here, you're not going to separate these 2 distinct orbits. Another problem with actions of the additive group is that invariants don't extend to the ambient affine, and so that's sort of a key feature of reductive GIT, is that often you can just work with the ambient affine or the ambient projective space and do everything there, but you can't for non-reductive groups, because if I look at this example that we had in part 3, and I take the locus where the last coordinate is 0, so this is a GA invariant closed subset inside A3, and now x2 will actually become a invariant function on X. But this does not extend to an invariant function on the larger space. So this is another problem. And in fact, so you could say, well, okay, maybe all of these problems are happening because we're not looking at free actions. So you could say, let's just look at free GA actions. But in fact, there exist examples of free actions of the additive group where the quotient is actually not even a scheme, just an algebraic space. And so you can see that if you want to construct reasonable quotients by non-reductive groups, it's quite tricky. And so one solution is to say, well, what's the easiest example of a quotient of a GA action? And that's when you have a trivial GA torso, so you have a slice for your GA action. And this is what is exploited by Birksey and Kirwan. They find slices of GA actions by using what they refer to as a grading by the multiplicative group. So let me just give a quick proposition about slices before explaining this grading. So if you take a GA action, then you can consider its derivation D. Sorry, I didn't write it clearly. And then if D has a slice, by which I mean that there is a invariant, sorry, there's a function S such that D of S is equal to 1. Then the GA action has a geometric slice, namely if you take the variety defined by S inside X, then actually X is isomorphic to GA cross S, and this is actually GA equivariant, and so the quotient of X is just S. Okay, so S is really a geometric slice of this action, and so you have a trivial GA bundle. So in particular, you actually get a geometric quotient, so it's a good quotient, and then this quotient is, yeah, indeed the spec of the invariant ring, so it's finitely generated because S is just a closed subvariety inside X. I wanted to give a few words on the proof, but I actually see that I'm kind of running short on time and maybe talking too much. So, well, the idea is very simple. You construct a homomorphism using your slice S. So essentially, you take this exponential TD, and now you evaluate it at t is equal to minus S, and then you can show that the image of this is precisely the kernel of D. This is not too much work, and we already know that the kernel of D is the GA invariant functions. And then using this, you can basically show that any F can be written as a polynomial in S. So you have that actually functions on X are polynomials in S with coefficients in the invariant ring. And so then this really gives you this description here, if you like. Let me just say, so that this slice business, you already see that actually you have a grading on OX, namely by the degree of S appearing here, right? This gives you a grading which is supported in, well, it's more natural to think about it being supported in degrees which are greater than or equal to 0, but I'm going to think about it as supported in degrees less than or equal to 0 by taking minus the degree of S. And this is this first notion of this graded condition. So the starting point of non-reductive GIT is like a converse statement to this. So what do I need to get a slice? And they prove the following. So if you have a GA action on an affine scheme, and you assume that the action extends to a semi-direct product of the additive group with the multiplicative group, where when the multiplicative group is acting on GA by conjugation, it's got a positive weight. This is also a kind of graded condition. It's sort of like a sign condition. And you also ask that this GM action, the flow down as t goes to 0 inside GM always exists. So what this actually means is if you consider the grading on the coordinate ring of X, then it's concentrated in degrees less than or equal to 0, because the weights have to be on the actual variety X have to be greater than or equal to 0 for this limit to exist. And then finally, there's another condition, which is not really to do with this graded conditions. These are sort of both graded conditions in a sense, but you ask that every GM fixed point has trivial GA stabilizer. Then they prove that actually there exists a GA slice, so in particular the ring of invariance is finitely generated, and you get a trivial GA quotient. And from this they formulate a projective version of non-reductive GIT. Yeah, maybe I can keep both of them up there together because they've really got analogs for part 1, 2, and 3. So now they have G, a non-reductive group, acting on a projective variety with respect to an ample linearization, such that there's a GM inside G, which is grading the unipotent radical. So again, what does this mean? This means that if you look at the GM action on the by conjugation on the unipotent radical, then its weights are always positive. And secondly, you have to assume something about the weights of the GM action with respect to this linearization. I'm not going to say precisely what this is, but you're basically fixing a variation of GIT chamber for the GM action. And then certain unipotent stabilizers must be trivial. This corresponds to this third condition here as well. And so 1, 2, and 3 here really correspond to 1, 2, and 3 here in this affine version. Then they prove that there is an open semi-stable set, and you get a good quotient of this, and this good quotient is projective. So this is really, really, really nice. But the difficult thing is that actually this condition that certain unipotent stabilizers must be trivial is very difficult to arrange. So actually the graded thing is not so difficult to arrange, but this unipotent stabilizer condition is really restrictive. And so the idea is that when this fails, you should try and blow up in a bit like the Cohen desingularization for reductive GIT quotients to make these stabilizers, well, as trivial as you can, so constant dimensional or something like this. And this is kind of the tricky point to this. But you're going to see that in a few minutes, I'm going to explain that by taking a more relative approach, you don't need to blow up. And it turns out that these two graded conditions, or these two here, are actually just naturally appearing in many examples. So many applications that you have to moduli theory involve these graded group actions. So for example, I wanted to talk about these moduli of hypersurfaces in weighted projective spaces. So if you look at the automorphism group of, for example, the weighted projective space P112, then what does this automorphism group look like? Well, you have a GL2 here, you have a GM here, but then you have a GA cubed term, which is roughly, so sorry, I should have said, I'm thinking about coordinates X, Y, and Z, and it's sending Z to Z plus AX squared plus B XY plus CY squared, where A, B, and C are in GA, so this is this non-reductive part here. But there is a one-parameter subgroup inside here which grades this action. So i.e. it acts with positive weights on this unipotent part. And then another example is you can naturally, rather than thinking about stable vector bundles, which have moduli spaces already constructed, you can think about unstable vector bundles. And these have usually a Harden-Arrowsiemann filtration. You can fix the type of that Harden-Arrowsiemann filtration. And in this case, the natural automorphism group to consider is a parabolic group. So you're sort of looking at automorphisms preserving a flag. So you get a parabolic group. And this is graded by the one-parameter subgroup that you use to construct this parabolic group. So that's also very nice because then this one-parameter subgroup is acting with positive weights on the unipotent radical. Another example is moduli of jets of maps. Where you also have a graded action, and then moduli of quivers with multiplicities. This is a little bit trickier because actually there is not a group that naturally grade. Well, inside the group that you have acting, there's not an obvious grading, but you can sort of extend the group and take a grading. So yeah, I can explain a little bit at the end. But let me explain this relative non-reductive GIT, which is joint work in progress with Eloise Hamilton and Josh Jackson. So actually we start out with a very sort of general question, which is, suppose I've got a morphism of varieties and a group homomorphism, and I've got an equivariant action of the, oh, was there a question? No. Okay, so I've got an equivariant action of the group homomorphism on my morphism of varieties. So what do I mean by this? I mean that G acts on X, H acts on Z, and then I have that, so if I act by G on a point X and I apply F, then it's the same as applying phi to G and then acting on the image of X under F. So, sorry, it's difficult to say in words, but it's easy with an equation. Yeah, and there's a special case of this, which is what we call a fiber-wise action, where H is trivial, so G is really acting on the fibers of F. Then we ask, given such an equivariant action, and does there exist an induced homomorphism, an induced morphism of varieties between good quotients of X and, Z, so Z should be quotiented by H. And these good quotients in general are going to be good quotients of open subsets of X and F. And so in fact, it's sort of easy to see when there might be, but in general, there isn't. And we were interested in this question actually in the case when G and H are reductive, but also in the case when G and H are non-reductive. And basically, the main reason that we were interested in this is we can actually generalize the non-reductive GIT to a sort of relative setting where you should think of this map F as flowing down under a GM action. So actually, this graded notion has a sort of relative setup as a, we say that if we've got a morphism, we say it's graded by a fiber-wise GM action. So GM is acting on X and it's acting on the fibers of F. If actually the fixed locus is Z, and the limit as t goes to 0 exists and is equal to f of x. So i.e. what we're really saying is this morphism is a cone, so you're just retracting onto Z. Then we say an equivariant action. So in this situation where we've got a group homomorphism acting on a morphism of varieties, we say this is graded by a copy of GM inside G. If GM gives a fiber-wise graded action on both the morphism F and the homomorphism phi, where here for phi, GM is acting on G by conjugation, so it's a subgroup inside G. Let me just interpret what these mean. So if you've got an affine morphism, so I'm writing X as relative spec of some sheaf of OZ algebras, then GM acting fiber-wise on F corresponds to a Z grading of this sheaf of algebras. And the fixed locus corresponds to the 0th graded piece. Then the action being the action being graded is just saying that it's concentrated in degrees which are less than or equal to 0, and the 0th piece is OZ. And similarly, if you have the morphism that we're interested in is actually this quotient morphism where you take G and you write it as its unipotent radical by some reductive part and you quotient out by the unipotent radical, then this is graded by a copy of GM inside G actually GM is central in the Levy part R, and GM acts on the Lie algebra view with positive weights. This is sort of generalization of the setup that they had. And an example of a graded action to keep in mind is if you take a parabolic group in a reductive group, so again, it's got a Levy factor and you can project from the parabolic group onto the Levy factor, then there's an equivariant action of this on the corresponding Lie algebras, and this action is graded. Okay. Then we prove a relative version of this key proposition, which says now if you've got you take a unipotent group and you twist it by a copy of the multiplicative group and you act on an affine morphism, then provided you base change basically to the locus over which the stabilizers are trivial, then you can construct a quotient by the action, which is actually a geometric quotient. It's just a Zariski locally trivial U bundle. Okay, I see that I'm running out of time, so I won't say anything about the proof. But maybe let me just move on to quivers with multiplicity, because I wanted to just end with a nice application. So this is joint work with Josh Jackson and Tanguy Vene. And so the classical construction of quiver representations over a field, so what we're talking about is linear algebra data encoded by a directed graph, involves you just, at each vertex you choose a basis, and then for each arrow you get a matrix. So the parameter space is a bunch of matrices, one for each arrow, and the symmetries that you're modding out by are products of, it's change of basis, so a product of general linear groups. And you can construct the affine GIT quotient, because this is just an affine space. But King shows that actually it's better to instead twist this action, as I discussed earlier, using a stability parameter to get a quotient which is projective over the affine GIT quotient and is only a quotient of some open semi-stable locus. Now, in the case of multiplicities, we now, on top of having the quiver and some sort of dimensions for our vector spaces, we also fix multiplicities. And now we're looking at, rather than a k-vector space at each vertex, we're looking at a free module over this truncated polynomial ring. And so what do you get? Well, you get, again, an affine space parameterizing these. And you have a group, which is the general linear groups on these spaces, which are non-reductive, acting. And this is precisely an equivariant setup. So actually you have a natural map from the space of quivers with multiplicity to without, so this map F. And you also have the non-reductive group. When you quotient by its unipotent radical, you get this group G up above here. So it's precisely the kind of situation that we were interested in. And then we use a character to actually get a quotient for this top action, so with multiplicities, which is projective over sort of the case where you take the trivial character, so where you take rho is equal to 0. And this is affine over the quotient that you get on the bottom locus, the King quotient that you get. And that in turn is projective over the standard affine GIT quotient. So we actually construct moduli spaces of representations of quivers with multiplicity using this relative approach to non-reductive GIT. And we really interpret this notion of semi-stability moduli theoretically using the Hilbert-Mumford criterion. So I see I've run out of time. So thank you very much for your attention. Yeah.